Hello everybody, welcome back to the Gregorius Maths video. Today, in this Lenten mathematics series, we're going to start chipping away at analysis. So we've already started looking at some dynamics and relativity, which I'll keep on looking at. And we've already started looking at some probability stuff, which again, we'll keep looking at. But another topic that's coming up is analysis. So we need to start chipping away at that too. And there's quite a lot of bookwork to get through, so better to start early than later. But the way I'll start is slightly less dry than, talking about continuity and series tests and whatever. I want to start by talking about this question which popped up in one of the example sheets. And the first part was to prove the Wallis product, which I'll go through. And then using that in order to get Stirling's formula or approximation for n factorial, which we'll look at in the second half of this video. And just for reference, the reason why this is all written down is because this is all recorded, as in I made this video before and I wrote all of this down, but the microphone ran out of battery, so my compromise between uploading it with no audio and like starting the whole thing again is recording it with everything written down already. Okay, so hopefully you are okay with that. Okay, so yes, the first thing we need to do is examine the Wallis product, or however you pronounce that guy's name. And the way we do this is we begin by just examining this family of integrals in, which are defined by the integral from 0 to pi over 2 of cos to the nx dx, okay? And if you do integration by parts, so you do the DI method, or however you want to do your integration by parts, I learned it via black pen, red pen, so there you go. You, after a couple of steps, obtain this recursive relation that n times by in is precisely n minus 1 times by I n minus 2, okay? Now, another thing to note here is that cos x between 0 and pi over 2 just takes values between 0 and 1, and therefore, as you increase the power, n, you're actually decreasing the integral because you're just multiplying by stuff that's less than 1, which decreases the value. And so therefore, I 2n plus 1 is less than I 2n, and so I 2n plus 1 over I 2n must be less than or equal to 1. Now, this thing right here is bigger than I 2n plus 2 over I 2n, simply because I 2n plus 1 is bigger than I 2n plus 2. Okay, but this right here, by the recursive relation that we found, is precisely given by 2n plus 1 over 2n plus 2. Now, this thing clearly goes to 1 as n goes to infinity, and so by the squeeze theorem, since we're bounded above by 1, but we're bounded below by this fraction, and they both go to 1 in the limit, this guy must also go to 1. And so we know that as n goes to infinity, I 2n plus 1 over I 2n goes to 1. All right. Why are we even bothering doing this? Well, here's why. I'll tell you why. Because let's take a closer look at this fraction, because there might be something more fishy, more interesting at play here. Indeed, if we use our recursive relation here, we can start to inductively set up a product. So I 2n plus 1 over I 2n, well, let's look at the top and the bottom separately. I 2n plus 1 is just 2n over 2n plus 1 times by I 2n minus 1 by the recursive relation. And similarly, I 2n is just 2n minus 1 over 2n times by I 2n minus 2. Now, just getting rid of the fractions on the top and the bottom, so multiplying the top and bottom by 2n, 2n plus 1, you get that this is just 2n times 2n over 2n minus 1 times 2n plus 1, brackets, times by this fraction. But we can just inductively use this relation, right? So we can just apply that to this fraction to get this in terms of I 2n minus 3 and 2n minus 4, and we can keep doing this until we hit I1 and I0. And so in the end, we just get 2n times 2n times 2n minus 2 times 2n minus 2, up until times 2 times I1. Okay, so on the top, we just get these pairs of even numbers multiplied together times by I1. And on the bottom, we get 2n plus 1 times by, and then we have two lots of 2n minus 1, and we'll get two lots of 2n minus 3, and we'll keep on getting pairs of odd numbers until 1, which of course doesn't really affect anything anyway. And then at the bottom, since we're multiplying by I2n minus, as in we keep going down the even numbers, we end up just at I0. Okay, now the good thing about this is I1 and I0 are very easy to compute. I0 is just pi over 2, and I1 is just 1. Now, this expression for the nth term, we can actually write in terms of powers and factorials and stuff. So, indeed, this nth term here is given by this expression, 2 to the 4n over 2n plus 1 times by 2n choose n to the minus 2. You might be wondering why that is. Well, okay, let's go through this. Firstly, 2n choose n to the minus 2 is just n factorial to the power of 4 over 2n factorial squared. So on the top of this fraction, we have n factorial to the power of 4 times by 2 to the 4n. So we have 1 times 1 times 1 times 1, times 2 times 2 times 2 times 2, and we keep on going up until n, and we have 4 copies of each. So in total, we have 4n numbers. But we have a 2 to the 4n. So all of those are multiplied by 2. So now we get 2 times 2 times 2 times 2, times 4 times 4 times 4, and we get 4 even numbers. So up until, so we get 2 multiplied by itself 4 times, we get 4 multiplied by itself 4 times, and so on up until 2n multiplied by itself 4 times, which is close to what we want. And now on the bottom, we have firstly, we have 2n factorial squared. So this 2n factorial squared is going to cancel out all of the, it's going to cancel out pairs of the even numbers that were on top. Keep in mind we had 4 even numbers, four like groups of 4, and this 2n factorial squared is going to cancel out 2 of them. So now on the top we do actually just have what we want. And on the bottom, well, what's going to survive is pairs of the odds. So 2n minus 1 times 2n minus 1, up until 3 times 3. And that's where the final 2n plus 1 comes in, this singleton at the end. So this expression here is precisely equal to this thing. But this limit right here, we've shown by the squeeze theorem goes to 1. So we get that this product times by I1 over I0 is equal to 1. But I1 over I0 is just 2 over pi. So multiply both sides by pi over 2, and you get that this limit right here is equal to pi over 2. Now, what this also implies is that if you rearrange this to, firstly, in the limit, this plus 1 does nothing, right? If you multiply by 2, cancel out the 2, do a bit of rearrangement, you get that the limit of this thing goes to 1. And if you just square root it, you get that you get 4 to the n, since 2 to the 4n square root is just 4 to the n, 4 to the n over square root pi n times by 2n choose n. The limit of that goes to 1. And so therefore we can say that 4 to the n over square root of pi n is just asymptotic to 2n choose n. And this fact right here is going to be very helpful in giving us Stirling's approximation. So let's see how on the other side of the board. All right, so firstly we define a sequence an given by n factorial times by e to the n all over n to the n plus a half, right? And this converges to some limit L, which I will not prove, but it does. So we're going to use this fact. And so namely, we're going to write 2n choose n in terms of an. And there's only two components here. We just need to write 2n factorial and n factorial in terms of an. So firstly, n factorial, if you just multiply and divide by the exponential, you just get that n factorial is an times n to the n plus half times e to the minus n. And 2n factorial is just a 2n times by 2n to the 2n plus a half e to the minus 2n. All right, that's fairly straightforward. And so when you plug this information in, you just plug in the expression for 2n factorial on the top, and then you square this and plug this in on the bottom. And after a bit of simplification, you get that this 2n choose n is just a 2n over an squared times by 4 to the n over square root of n times by root 2. And so if you just bring this to the other side, you get that 2n choose n times by root n over 4 to the n is just a 2n over an squared times root 2. All right? And now this is where we use the fact that this is true, that these two things are asymptotic. Because now we say that in the limit, this thing right here will just go to 1 over root pi, right? Because there's a missing factor of root pi. So this thing in the limit just goes to 1 over root pi. And this thing right here, well, we're saying that this an goes to L. So on the top, we just get L, and on the bottom, we get L squared. And we're multiplying by root 2. So in the end, we just get root 2 over L. And so indeed, what do we get if we rearrange this is that L, the thing that this goes to, is in the limit is just root 2 pi. Namely, we get that n factorial over e to the n over n to the n plus a half in the limit as n goes to infinity goes to root 2 pi. And therefore, if you rearrange this to get n factorial by itself, if you multiply by n to the half, you get this. If you then multiply by n over e to the n, you get that. Precisely, what you get is that n factorial is asymptotic to 2 pi n times by n over e to the n, which is Stirling's formula. And so, in this way, you can obtain Stirling's formula right from the Wallis product. And yeah, I hope you enjoyed this. This was my fun little beginning into perhaps the more dry elements of analysis, or maybe you find them interesting. I mean, there is some stuff in analysis which is interesting. We'll dive into that in later videos, but for now, assuming the microphone is working this time, I'll see you soon. Bye-bye.